Good morning. I should start out today by saying that there are several free umbrellas in the front. Just kidding. $5 each. So I thought I would continue today talking about nanofabrication, but in particular a certain application of nanofabrication in unconventional solar cells. So we're going to talk a little bit about how conventional p-n junction type solar cells work, then how so-called excitonic solar cells work, which is relevant to nanoengineering because most of the types of nano-enabled solar cells operate by this sort of third generation mechanism. And let's begin. So whenever a professor or any scientist gives a talk or a lecture that's even peripherally related to the energy challenge, he or she gives a few factoids that serve to motivate the research, but ironically depress the audience. And this is my favorite. That more energy in the form of sunlight strikes the Earth in an hour than is consumed by human activity in a year. And many of you may have seen this particular factoid, but it's worth sinking in to get the gravity of this idea. However, sunlight is dilute. Even at your best, you're only going to get a day-night average flux in North America of about 200 watts per square meter. So that sounds like kind of a lot. You know, that's enough for two crappy 100-watt incandescent light bulbs per square meter. Hopefully you're all installing CFLs or even better LED lights in your houses and apartments now. But our solar technology can't capture all 200 watts, right? We can only get 10 to 20% of it depending on the efficiency of the solar photovoltaic technology. However, land area is not only a constraint for photovoltaics, it's actually a constraint for all alternative energy technologies. And sometimes it's even said that that solar energy is too dilute to capture. We must need a ton of land. Is it a deal breaker for solar? So if you look at the energy that you can capture with 10 to 20% efficient solar cells, maybe 10 to 20 watts per square meter. Okay, so there's our baseline. Wind. Wind we don't think of as requiring land area, but it really does because you can't put one windmill right in front of the other because why not? It's going to block the wind. So you have to space them out. The good thing about wind and solar is that you can put them in the same place because the shadow cast by a windmill is not very much. But once you space these optimally, you get about 1 to 2 watts per square meter, so an order of magnitude lower than solar. And by the way, I took this analysis from Saul Griffith, who is an entrepreneur who works in energy and low-cost eyeglasses and all kinds of cool things. You can find the video here. I actually saw this lecture in person when he gave it, but it's a really good lecture from sponsored by the X Prize Foundation, which many of you may have heard of. Hydroelectric power, a nice green source of energy, unless you happen to have been an animal that lived in the Hetch Hetchy Reservoir before they flooded it permanently. So hydroelectric power we don't normally think of as having land area requirements, but it really does. So if you take, for example, I used the example of the Hoover Dam in a few lectures ago, but if you take the energy that the Hoover Dam produces and you divide it by the area of Lake Mead, you get about 3 watts per square meter. So you need to build up this reservoir of this lake that by gravity spins the turbines when it goes through a dam. And also I should say that we've done this pretty much everywhere in the US where it's feasible to do it. Biomass, assuming we had a 3% efficient algae, I don't think we do, that would give you 3 watts per square meter. So I don't mean that the sugars produced by biomass, which is what we use now, I mean all of the chemical bonds produced in the proteins and lipids and carbohydrates. You just take the algae, you dry it out, and you shove it directly into your gas tank. This is the energy per unit area that you could maximally expect to derive from biomass. Corn ethanol, so this is just the sugar content of a not particularly well sugar producing plant. So it's just the juice, it's not even just the juice within the yellow part. It's not the husks or the stalk or the cob, if you will, or even the hard skins that are made of cellulose, which are not very easy to digest and ferment and distill into ethanol. So now we're 2 orders of magnitude below solar here. They say that this is good energy politics, but bad energy policy. Hydrothermal flux, we get about 57 milliwatts per square meter. Now, of course, this is not at Yellowstone National Park, where it's much higher than this, but you wouldn't want to dam up Yellowstone National Park and put a turbine on top of Old Faithful and so on. And this is the integrated hydrothermal flux from the core of the Earth over the entire surface of the Earth. So there are places where it's, of course, desirable to do this. Has anybody ever seen a plot like this? This is a really interesting representation of the way in which energy is produced on the left and consumed in the middle, and the output on the right. So if you look, and I put 2005 deliberately. It's the year that I started grad school, and I told my advisor that I wanted to work in solar energy, and my advisor said, look at this plot, and then look at the contribution of solar, 0.06%. If you made a small change here, you would make a very tiny change in the grand scheme of things, whereas if you made a small change in fossil fuels, say the way in which energy is extracted or used from fossil fuels, you would make a much larger absolute difference, even with a much smaller percentage difference in these areas, just because you're starting out with a much higher baseline. So if you look at this, let me just explain what's going on here. This is, these are the units, estimated energy units in quads, which are quadrillion British thermal units, just about the most intuitive unit that we can think of. But anyway, it is intuitive here because it's almost adds up to 100%. So 1 quad is 1%, and this was in 2005, and we got a third roughly from petroleum, coal, natural gas, really 40%, 20%, 20%, and then the rest from relatively smaller renewable or nuclear is not renewable, but at least it's carbon free. So if you look at all of the energy that goes into electricity, industrial uses, commercial uses, residential uses, transportation uses, of course uses petroleum, because petroleum is perhaps the highest value energy source because it's transportable and you can do anything with it. It's not as valuable as electricity generation, which you can also do anything with, but generating electricity is very inefficient. So for example, once all of these lines and these lines and bands go into these uses, the gray stuff coming out is either useful energy or wasted energy. And this is energy due to inefficiency of generation and the processing. And what you can notice here is that the wasted energy is more than half. So more than half of these quadrillion British thermal units are wasted. Okay, so I was going to tell you that, well, this was kind of depressing what my advisor said about the 0.06%, but you've heard of exponential technologies. It's like the biggest, it's kind of the buzzword, right? How many doublings will it take to get to like artificial intelligence or completely green energy? So if we fast forward a little bit, this is 2013, and solar has gone up by a factor of 5. Now, installed capacity in the world is increasing at a rate of about 60% per year for the last approximately decade, which is quite incredible. In fact, in the European Union, at least what was formerly known as the European Union, the installed electrical generation capacity was greater for solar than any other source, and that's been true for the last several years. Okay, so here's 2013. Notice our total energy usage has gone down between 2005 and 2013, mainly driven by the reduction in the overall amount of coal and petroleum that we're burning, which is good. So the U.S. is doing something right here in energy. Yep.
I noticed there's actually an increase in the share of rejected energy. Could that be attributed to a decrease in fossil fuels or something else?
So increase in rejected energy.
Right, as a share, it's actually objectively more, but it's also more of a smaller total. So
yeah, that's a good point. I'd have to crunch the numbers and figure out which parts are decreasing in efficiency more. Yeah, it's a good observation.
Are you posting these slides as well?
Yeah. So if you keep your eye on solar here, so if you go into the Lawrence Livermore National Lab website, you can download all of these charts for as many years as they've been making them, and you can make your own plots and stuff. That's what I do on the weekends. 2014, we go up by another 100 trillion BTUs in solar, which is nice. And then the latest year on record that they had was 2015, and we're up by another 100 trillion British thermal units. Coal has gone way down, by the way. Remember, we started, it was 22, 23 quads, and energy has kind of leveled off in the high 90s, but it's not 100 anymore. So a lot of this reduction in the amount of energy, amount of fossil fuel use has really been driven by increases in efficiency in transportation and industry, among other increases in efficiency. Okay, nevertheless, yep.
So when we're talking about rejected energy, what does it mean?
So the question is, what does rejected energy mean? Rejected energy is the inefficient conversion of a primary energy source to the final usage. So in the case of an internal combustion engine, we might have a gigajoule or 100 gigajoules of gasoline that we put into the car over some amount of time. But maybe the amount of energy in the form of work that we get from moving the car from point A to point B over that same amount of time might only be 30 gigajoules or something. And in fact, you can see how inefficient transportation actually is. And even in 2015, the electricity generation, 0.03, this is the Teslas and the Leafs and the other EVs. Nevertheless, we still need a damn lot of land area. So this slide is kind of a famous slide that I took from Nathan Lewis, who's a professor at Caltech, and he put this it's an old image, but it's still more or less true that if we took the solar panel technology that we have today, that's maybe 10 to 20% efficient, and we had to cover some land area with it, we would need to cover approximately this amount of land, which is 2% of the contiguous United States. Of course, you would never put it in a central location because of all the losses that you would get by transmitting the energy. So to think about something to compare this to something that's distributed, it's about 3 times the size of Massachusetts. Massachusetts is not distributed either. It's 10 times the area of all the rooftops. So even if you covered all the rooftops, you still you would get there. You'd still need 10 times more rooftops to get this. But this is about the size of all the roads. So the size of the roads covers actually quite a huge amount of area. So you can picture this is the amount of concrete that we've poured, in asphalt that we've poured onto the ground. So we've done civil engineering projects on this scale before, but you would still need quite a lot. Now this is to get all of the primary energy, not just the electricity. The electricity is high value energy, and it costs maybe 20 cents per kilowatt hour or whatever. It didn't cost the utility that to make it. It cost maybe more like 2 or 5 cents or something per kilowatt hour, depending on what their energy source was. But this is all the energy. This is assuming we could take all the energy, convert it to fossil fuels that could be burned 100% efficiently. So when somebody tells you, well, today's solar panels, that are produced so cheaply in China will just replace all of the research in solar photovoltaics. That's complete BS, because that's only electricity. That's only to reach price parity with electricity, which is only a third of energy usage. In order for it to be for you to use it to heat your house and run your car and run factory equipment, you have to be able to convert you have to be able to use electricity for the primary energy source as well, which involves solar fuels and batteries, but at the root of it is making better photovoltaic devices. And they literally have to be, how cheap do they have to be? They have to be no more than 10 times the cost of paint. So it was like 10 times the cost of paint. 10 times the cost of paint is the cost of carpet. So you need to have these wall-to-wall carpets that are actually sophisticated semiconductor devices that can absorb light and separate charge and generate photo voltage. Despite the oldness of this reference, this calculation is still more or less accurate. So do we have any technologies that are kind of similar to paint? And I alluded to some of them before. Remember I told you that you could make a solar cell out of beta carotene and chlorophyll if you purified them enough. It's a crappy solar cell, but in principle it would still work. Well, there are purpose-designed materials that can be used for organic photovoltaic devices like this type of polymer. It's called a conjugated polymer. It's called conjugated because it has alternating double and single bonds along the backbone. And then you need some kind of electron acceptor, which could be another polymer. It could be a quantum dot. This could be a quantum dot. They work by the same physical principles. And it could be a dye-sensitized solar cell. So you could have this material in concert with a redox couple and an electrolyte that was grafted to a titania, it's TiO2 nanostructured surface, and you can make a solar cell that way. A lot of different ways you could do this. You need a donor and an acceptor, and they need to be cheap materials. They need to have a high absorption cross-section, which means that when I talked about light-matter interactions, that part on this board where I said nothing happens when light is absorbed, you don't want materials where nothing happens. You want materials that you can make very thin so that they're very absorbing at the same time. And these materials cost on the order of $1 per square meter. So just research quantities of the material are already in the range that we need. So paint is about $1 per square meter. This does not include fabrication costs or anything like that, but it's a step in the right direction. Now there are a series of new inventions over the last couple of decades on roll-to-roll printable solar cells. So this includes organic solar cells, quantum dot solar cells, perovskite solar cells, which operate on a little bit of a different principle, but a lot of the same production techniques are applicable. And what the good thing about these processes are that they're kind of reminiscent of things that we already make on large areas like newspapers. And they have a lot of characteristics like roll-to-roll manufacturability, flexibility, portability, collapsibility, wearability, even for portable off-grid types of applications, the ability to bond to curved surfaces, and extreme thinness. And all of these things are something that you can't do with a normal polycrystalline silicon solar cell. And this is all dependent on mechanical properties of these materials, which is something that actually we work on in the lab. Okay, now this is not how the principal solar cells work, but this is how a conventional solar cell works. Conventional solar cell, which is 99.9% of all solar cells that are out there, and that may ever be out there depending on how technology develops over the next few decades. Basically, you have 4 components, and you can read more about this. I can give you some references if you'd like. But basically, you have a back electrode, a P-type semiconductor, an N-type semiconductor, and another electrode, which is often called the finger electrode, which collects charges from the N-type material. What's the difference between P-type and N-type? P-type means that it has positive charge carriers, that the charge carriers are positive. N-type means that it has charge carriers that are negative. That's intrinsic. So before we even make a device, you can have what's called a P-doped semiconductor or an N-doped semiconductor. How do you P-dope it or N-dope it? Well, silicon has 4 valencies, right? It forms a tetrahedral structure in a single crystal, just like carbon. If you put in atoms in the lattice that have either fewer electrons or more electrons than silicon does, then it creates either a hole or an electron. And the hole and the electron are not formally positively or negatively charged. They're just a space in the lattice that's missing an electron, but because you're doping it with something that has fewer than 4 valence electrons, like boron, it also has 1 fewer proton, so that the charges are still balanced. So a hole, this is confusing because it's different than what we were talking about before, but I'm not making this up. There really are 2 sets of nomenclatures here. The hole in the P-type, which are holes in the valence band, are electrically neutral because there are there's not an extra proton, so to speak, to make these positively charged. I'll get to your question in a second. The N-type has something that, you have the silicon that's doped with something with 5 valence electrons, like arsenic or phosphorus. There's 5 valence electrons. One of those electrons doesn't know what to do, so it floats around. It's a charge carrier, but the total system is electrically neutral because phosphorus or arsenic indeed has another proton. Is that okay? Question?
So another way of saying that, could we say that the number density of electrons is higher in N-type than pure silicon and lower in a P-type?
The question was, can we say that the number density of electrons is higher in N-type and compared to pristine silicon? The answer is yes. We can't say that. Geometrically, though, in the lattice, these excess electrons and holes, which is really the absence of an electron in the lattice, they would like to equilibrate. And they equilibrate even though they create an electrical dipole or electric field across the gap. So if you take these 2 sides and you push them together, notice that here I have a blank spot in between. You take them and you push them together, whoa, a bunch of shit happens. What happens? The bands bend because the Fermi level, or the electrochemical potential of the whole system, equilibrates because you stick them together, And the electrons sink and holes float, right? Electrons sink down here, holes float up here because they are consumed by because a couple of electrons go into the p-type material. Now, ironically, what happens as a result of this is that the p side becomes negatively charged and the n side becomes positively charged. But this layer here only penetrates some small fraction into the material. Because there's a balance, right? There's a balance. Things don't like to be electrically charged, but they like to fill unfilled valencies too. So there's a little bit of a push and pull effect here. What we get is then an electric field that develops within the semiconductor device due to, and this is called a diode, by the way, a field that develops within the semiconductor device where the electric field points from positive to negative, thusly. Okay, now what happens? Just so you can kind of see this animation. Whoa, 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 whoa. Fascinating. One more time for emphasis. Whoa. Okay. Now light comes in. Light comes in, and light comes in with a lot of energy. And what does it do? It strikes an electron, or it strikes an electron in the valence band of, in this case, the p-type material. It could be the n-type material, but we'll just say it's the p-type material now. And then that electron is promoted into the conduction band. And then it's thermalized to the band edge, just as we talked about before. And critically in this case, because silicon is a high dielectric medium, the Coulombic force holding the hole and the electron, we'll go negative charge and positive charge together. The Coulombic force holding them together is weak because the dielectric constant of silicon is high. What is a dielectric constant? Dielectric constant is the extent to which a medium can screen electric charge of an adjacent electric charge. So it reduces the force between electric charges. It increases the amount of charge that we can have without increasing the electrostatic potential energy too much. And as a result, the hole and the electron are unbound to each other. So dielectric constant is high enough, the hole and the electron can swim around wherever they want. Eventually, they'll get drawn into this field here, and they separate. And this happens enough times, and they separate to opposite sides of the diode produced by putting the two unlike semiconductors together. Now, this accumulation of charges on the front and back of the solar cell is called the photovoltaic effect. So this is a photovoltaic cell, and when you connect these two electrodes to a load and continue to shine light on it and continue to replenish these electron hole pairs, the current will pass through the load and light a light bulb or a Tesla, or charge the batteries in a Tesla or something, and then we'll go back into the other side, and that'll be the steady state. Okay. In contrast, an organic solar cell, or a solar cell based on a quantum dot, or any solar cell based on these highly absorbing but rather crappy charge transporting solution processed semiconductors, operate by a different mechanism. In this case, we have a p-type and n-type donor, but I don't like using p-type and n-type because it's not exactly the same thing. We're not doping it with unfilled valencies. It just happens that the p-type material is better at transporting holes and the n-type material is better at transporting electrons. So we prefer electron donor and electron acceptor. These are the Fermi energies and work functions in an isolated metal. They're equivalent of a high work function electrode, and by high I mean more negative because vacuum level is somewhere here. So high means the absolute value, even though this one's low compared to this one. Basically everything I'm saying in this lecture, convert it to the opposite and you'll get to the meeting. This is the high work function electrode. This is the low work function electrode because it has a smaller absolute value compared to the vacuum level, which is 0. This might be, say, -5 electron volts. This level might be -3 electron volts, and 0 is here. This is the highest occupied molecular orbital. It's sort of like the valence band. The LUMO is the lowest unoccupied molecular orbital. Okay, so this is the open circuit condition. We haven't connected this to a load yet. When we connect it to a load, the electrochemical potentials of the electrodes equilibrate, and that produces a weak electric field in this direction. And because the positive end of the electric field is on this side, the electrons become lower in energy on this side and higher in energy on this side because of the way that the electric field points. Remember, electric field is positive on this side and negative on the arrowhead side. Okay, so now what happens when light comes in? Light comes in and it promotes an electron from the highest occupied to the lowest unoccupied molecular orbital. Comes in and it makes this electron-hole pair. Now, in contrast to the conventional solar cell, the electron-hole pair in one of these sort of cheap third-generation cells is bound, because this is a low dielectric constant medium compared to silicon. This is like basically the dielectric constant of like oil, so 2 or 3 or something like that. These charges feel an immense pull from each other, and they're stuck there. So most of the time what happens, because these are really crappy materials, is that these, these excitons, they're called excitons. It's like an excited quasi-particle. It can float around, and the vast majority of the time, vast majority of the time when the layers are really thick, the exciton collapses onto itself and either releases heat or it might release a fluorescent photon. So we call this as unproductive. This is decay, this is loss, fluorescence, whatever you want to call it. Sometimes, however, the exciton is lucky and it reaches the interface between the p-type and the n-type material. And now this electron here sees that it can decrease its free energy by jumping from here to here, and this is called a photo-induced electron transport. I'm going to anticipate your question. Why doesn't it just go down? Oh no. Okay, different question.
So the exciton itself, is that, you said it has a high dielectric, or low dielectric, so the charge is basically stuck in place with its original nucleus. So is the particle itself moving in the medium? Or the
particle itself can move in the medium, and it can diffuse on average, depending on the semiconductor material, around 10-ish nanometers before it has to do something.
So these are very small scale.
Yeah, and they actually, they move around by quite complex mechanisms, by fluorescence resonance energy transfer, by other physical mechanisms where you get an excitation here that transfers its energy to another part of a molecule or a different molecule.
So it's not crystal structure, it's almost like a gel.
So the question is it a crystal structure or a gel? These materials can be crystalline, but they also work if they're amorphous too. Some of them will work if they're amorphous. And you have two choices. Most of these materials, at least in the organic field, are polymeric. So you can either transport the exciton along a polymer chain, or you can move it from one polymer chain to another. Yep.
Why doesn't the exciton just go?
So the exciton, sometimes it just decays, but if it reaches an interface, it might move over here more easily, because sometimes there's a reorganization energy associated with going from the ground state to the excited state, and it might take more time on the part of the molecule to reorganize its structure to accommodate the ground state. than it does simply to transfer. So it might take, I'm going to get the time scales wrong, but it might take a nanosecond to reorganize in a way to go back down here, but it might take a femtosecond to go over here. Yeah.
In this case, like kinetics would beat out like energy level.
Yes, in this case, yeah. So kinetics are your friend in this case. All right. So now the electron and hole, the exciton splits. So now you have a hole here and an electron here. These electrons and holes are different from the electrons and holes in the conventional semiconductor. In this case, the hole is an absence of an electron, but it's actually positively charged because the lattice in which it originally sat had an extra positive charge, whereas in the conventional semiconductor, the p-type material is doped with like boron or something, which has one fewer proton, so it's not charged. In the case of these organic and quantum dot or dye-sensitized solar cells, sort of third-generation solar cells, the holes in the electrons do actually have a charge. Okay, so now the holes in the electrons safely on the material that's good at transporting the positive charges and the material that's good at transporting the negative charges. And by the way, we have this built-in electric field due to the equilibration of the electrodes. So now what's going to happen is that the charge carriers drift. They drift toward the high work function electrode and low work function electrode, and if they are connected to a load here, they'll power the load. There's a little bit of nomenclature here. The exciton diffuses because there's no electrical bias, but the charge carriers drift. So diffusion versus drift. And that's a little bit of semiconductor nomenclature for you. Okay. How do we measure these things? So these are highest occupied, lowest unoccupied molecular orbitals. This is our electron donor and electron acceptor. This is kind of the quintessential nanoparticle, single molecule nanoparticle. It's the buckyball, and it has this junk on it because this is insoluble or very poorly soluble by itself. But since you want to process these things like paint, you have to put some junk on it. Okay. The way you make this type of device is you have a transparent electrode, or you have a glass substrate, you have a transparent electrode, you have the composite of these two materials, the p-type and the n-type, that are mixed together, and they're not a nice bilayer like I showed you in the last slide. They're actually mixed together. Why do we want to mix them together? I hinted at it, but we'll get to it in a second. Then you have your low work function electrode, which is like aluminum or some other material. This says this is for eutectic gallium indium. Don't worry too much about that. Don't worry at all about that. Okay, this is a plot of how you characterize a solar cell. So what happens is that the electrons are coming out of the solar cell this way, and the holes are going out of the solar cell this way, as I've indicated here. And what you do is you hook this up to a source measure unit, where you apply an increasing bias from negative to positive against the solar cell. And what you do is you do it in the dark, which is this gray curve, and in the light, which is this black curve. And what you're essentially doing is measuring the power that it takes to push the charge carriers back into the device. So they want to come out, and you're pushing them back in, and you're measuring the voltage and the current that it takes in order to stop doing that. That's how you characterize the device. So what this ends up being is the electrons are still coming out of the device, still coming out of the device, still coming out of the device. You get to a point which, and then you cross this point on the y-axis, which is called the short circuit current density. It's the amount of current that comes out when there's no external load, so no voltage is applied on the y-axis, because the voltage is 0, right? So there's no bias applied here. This is the short circuit. It's what you would get if you took a thick copper wire and you connected it to both sides of the device. Low resistance, nothing opposing the flow of current. You keep pushing the electron. You keep trying to stuff electrons in this way now. keep trying to stuff them in, and eventually the electrons stop coming out. They say, okay, I give up, and then the current starts going way up because now you're forcing the electrons into this material, then into the PCBM, which is the buckyballs, then into the polymer. And since those are better at carrying the electrons, the current is much higher in this direction than it is in this direction after you've kind of forced the solar cell into submission. Does that kind of make sense? The point that maximizes the current and the voltage is called the maximum power point. The x-intercept is the open circuit voltage. It's the amount of voltage that you get before you connect it to any load. So short circuit, when you connect it to a load that has infinitely low resistance, and the voltage that you have when you connect it to something that has infinitely high resistance. The point between VOC and JSC that maximizes these quantities is the maximum power point. Now, the maximum power point is always less than the pure product of VOC times JSC because there are inefficiencies in the device. Ideally, you'd want this curve to go all the way up to here and then as straight up as possible. And that never happens, but you can get in the high 90s if you want. I made this device using organic materials, so it does not work that well. But good quality silicon solar cells have a very high what's called fill factor, which is the difference between the square carved out by the maximum power point and the axes and the pure product of VOC times JSC. This fraction is about 60% of the total, and that's not great, but it is what it is. Okay, so we started talking about this based on wanting to do nanofabrication and how we could improve devices by nanostructuring materials. So I hinted at this before, but the donor-acceptor heterojunction is limited in a sense if it's flat because the exciton diffusion length is about 10 nanometers, but you need about 100 nanometers to absorb all the light. So if you have a planar heterojunction between the two materials, this is inherently inefficient because a charge carrier produced up here, an exciton produced up here, will probably collapse before it reaches the interface. So as a result, what you do is you make, and this is a very poor drawing, but it gets the point across. You take, I can make spheres and circles in PowerPoint. Anyway, you can take the two materials and mix them together, and you increase the amount of interfacial area, and you make the junctions a lot closer to each other. So you increase the probability that one charge carrier, or that the exciton is going to break apart into the free electron and free hole. The problem here, though, is that you also lose control over which material is in contact with which electrode, which can cause problems. So the ideal structure is to have something with an interdigitated architecture where the lateral spacing is commensurate with the exciton diffusion length, and the thickness is the thickness at which light absorption is optimal. So you can use soft lithography to do this. And this work was done by Richard Friend's group and others at the University of Cambridge, where they took these two materials. This is the electron donor and the electron acceptor. And what you do is you take a silicon mold that you've made by electron beam lithography, and you press it into one of the polymers to make these nanostructures. And then you take this and then you press it into the other polymer to make this interdigitated heterostructure. They say three-dimensional view. This is really nothing like what they were successful in actually making, which their structures are much less high aspect ratio, you can see, but they did kind of get these notice what they did here. Yeah, so when Notice the disparity between the values on the y-axis and the x-axis to make them look really, really tall. Anyway, okay, enough said. It's on YouTube. Okay, so they made these structures, and what they showed, I don't have the slide, but what they show is that you get a much better IV curve with the structuring than without it. And that makes sense, right? Because you have more interfacial area, but you also have control over which material is in contact with which electrode. Now, what about a structure that can form this automatically? So we talked about top-down and bottom-up fabrication. Now there are, we'll talk about polymers more starting Friday. Actually, we'll move into talking about intro to polymer science. The top-down nanofabrication is e-beam lithography and photolithography and soft lithography and all of these lithographic techniques where you take materials and you mold them and shape them and etch them and sculpt them. Bottom up is where you take a material itself that has some thermodynamic driving force to form the structure that you want automatically. It's kind of like computer chips on one hand versus biological systems on the other hand. One type of sort of quintessential bottom-up type of structure is a block copolymer. So polymers, for reasons that I'll tell you about next week, want to separate when you try to blend them. So polymers don't like to mix, basically for the reasons that other things don't like to mix, but they're polymers and they have even a stronger driving force not to mix. But if you covalently link them, say here, two structures that don't want to mix, as you alter the amount of the blue side from the mustard orange side, you have more of the yellow stuff over here, and you go from a cubic to a hexagonal to a gyroidal to a lamellar structure. Then you have the inverse gyroidal, the inverse hexagonal, and the inverse cubic structure. And this is well known. These are the structures, and as soon as you reach a certain mole fraction of one block versus the other, you kind of snap from one nanostructured morphology to the other, which is pretty cool. These domains are on the order of a few tens of nanometers. It could be 10 nanometers or 100 nanometers depending on the material. Okay, so what if we took the lamellar structure or the hexagonal structure and we put that between electrodes with different work functions? Could we make a good device? It turns out that this idea has been around in the literature for a very long time and hasn't quite worked out. Most likely because the materials that make good block copolymers tend to not make good organic semiconductors. But I want to show you some of the structures that are possible. Block copolymers are used ubiquitously in engineering plastics and elastomers, and increasingly in microelectronics fabrication. So you want a low K dielectric material. We talked about this a little bit before. You can make air gaps, for example. If you have polystyrene block PMMA and you cast this film, this is a hexagonal microstructure, but it's sort of looking from the top down. So these little circular microdomains. What's amazing here is how well registered this structure is. So this is several microns across, but you can draw a line. This dot here, straight line all the way across, straight line all the way down. And this is the structure that you get automatically. You would think that you drew this in a computer, but this is the structure that you get by having polymer chains of precise lengths that don't want to intermix, but they can't get away from each other because they're covalently bound in the center. You can get these things to grow within channels or to bend around curves. This is the lamellar geometry, but it's sideways. This is kind of the sideways lamellar geometry. You can make kind of cool brain-looking patterns. These are, you can make especially high aspect ratio features, and what's interesting is if you have a photoresist pattern, you can put block copolymers inside it that have features that will self-assemble to be smaller than the features that you can make by photolithography, because the because the block copolymers have molecular dimensions, and in principle you can make them very small. So we have. I think I want to stop there, and I think I want to say good night to the unconventional nanofabrication part of the course, and we'll start on polymers on Friday. Thank you very much for your attention.